Hi everyone. I'm a second year PhD in Johan's group, and today I'll talk about like graph shift operator for power system applications. So first, what is a graph shift operator? So a graph shift operator is just a matrix that like defines the structure of the graph, and the only the property the matrix needs to satisfy is that when there is no connection between two nodes, for example, the entry for that edge or the entry for that link in the matrix should be 0. So you can have, when there is a connection between two nodes in the graph, then you have a value, a real value in the matrix. So GSO or a graph shift operator forms the backbone or a very important component of a graph neural network. And what is typically used in the literature for neural networks is, so you can use the adjacency matrix, or you can use some other matrices that fulfill that graph shift operator property, like the Laplacian matrix, normalized Laplacian, or normalized adjacency matrix that has made famous by this work by Keith and Welling. So these are just some examples of matrices that are commonly used as shift operators in graph neural networks. Before I go further, maybe just some basics on graph neural network and what the shift operator or the graph shift operator actually does. So a general graph convolution layer is like this. So you have the graph shift operator, which is the matrix S. Okay, maybe it doesn't.
When the screen absorbs the lasers.
Yeah. So which is the matrix S. So if you're aggregating messages from several ops away, the K represents the number of ops. So number of ops means how many neighbor away you're aggregating information. And you have, in the case of a graph neural network, which is what distinguishes it from a graph filter, you have a learnable weight matrix. So that's like a parameter of your graph neural network in the case of a graph neural network. And of course, in the case of a graph neural network, you pass everything through a nonlinear activation function. So that's the nonlinearity that you have in that equation. That can be like a ReLU function, a tanh function, and so on. So you can see it's very similar to a graph filter, a graph neural network, a graph convolutional layer in the case of GNN, and a linear graph filter. And then I would also briefly talk about like message passing graph neural network, which is like the most popular variant of graph neural network. The architecture basically follows 3 steps. So you have a message construction, you have a message aggregation, and then you update the message. To construct a message, you can use fancy things like NLP. So if you combine the feature vector of a node with feature vector of the neighboring node, and if you have edge information or edge features, you can concatenate all of that, use it to construct a message. By passing it through an NLP, aggregate information from all the neighboring nodes. So that's what is signified by J there. And then update that message. You can also update the message through an NLP, for example. And then Jochen has talked about application of like graph neural networks in power system. So if you have a power system, in this talk, I'll focus on like transmission level power system, so maybe a little bit different from what he described. So if we have a power system in this form, this is just a simple test system IEEE 9 bus. We can construct the graph equivalent where the nodes of the graph signifies the bus in the network. So for example, in a 9 bus system, you would have like 9 nodes, and the edges would just signify the links or the transmission lines, let's say, between the various buses. So you can transform a power system network into the equivalent graph. And now we have the question of what constitutes like the best graph shift operator. And there is this quote from this book that says, you don't have any best matrix that can act as the best graph shift operator. And basically your choice of graph shift operator should be informed by the property that you're interested in, the property you want to preserve. So in this case, we would like to choose a matrix that best fits the property we need. And something we're particularly interested in power system is the stability of the GNN, or of the graph neural network, to topological aberrations in power systems. So topological aberration in power system can be induced by planned and unplanned outages. So there is this notion of n-1 contingency in power systems, which simply means that a line goes out. So if a line goes out, like you have a link loss, could be because of like a planned maintenance, or like a thunderstorm simply takes out a line. So when that happens, you have a small change, but still a change in your power system topology. And what system operators typically want is that your system is robust to n-1 contingencies. At least that's the standard for now. So if you lose a line, you want to make sure that the system doesn't suddenly collapse, that the system is still able to deliver power. So in this case, we're interested in if there is a perturbation to our S matrix, because if you lose a line, or that means an edge disappears in your graph. So your graph shift operator, one entry there is going to become 0, for example. So how stable is the graph filter? So that is an interesting question we want to pursue. And in the literature on graph filter, there are like these two filters. We talk of a Lipschitz filter and an integral Lipschitz filter. So in the case of a Lipschitz filter, you just have a filter whose response is at most linear. So if you look at the eigenvalue or the spectrum of the graph, the difference between one and the next is at best linear in terms of like the filter response. But if you talk of the integral Lipschitz filter, you have a filter whose response is flat at I eigenvalues. So at best sublinear, in the case that for I eigenvalues, the filter response doesn't change very much. So we would prefer that the filter that is length is integral Lipschitz, because that's more stable to stochastic perturbation. So there is this theory derived in this work on stability of graph neural networks to stochastic perturbation. And the theory says that if you have a graph and a subgraph, so the subgraph in this case is just a modified graph. So think of the same graph that has lost an edge. So if we have a graph and a subgraph, the expected difference between the GNN model can be bounded by this derivation of this formula. So the C in the formula is a constant, so the Lipschitz constant that is dependent on the choice of the graph shift operator. It's also dependent on some other properties like the number of layers of your graph neural network and so on. But it's dependent on the choice of the GSO, where the P is the probability of link loss. Now, if we look at this theorem, what we can really affect is the C, because we don't have control so much over the probability of link loss, at least in the case of power systems. Let's say it's not a planned outage. So we want a choice of GSO, for example, that minimizes the C, or that makes the constant smaller in this case, so that the difference between the GNN outputs for the two graphs or the two cases are as small as possible. So the filter in the case of, like I mentioned before, the filter in the case of GNN is learned, right? So the filter is not explicitly designed like in the case of a linear graph filter, where you can choose the filter that you want. The filter in this case is given by the weight matrix of your GNN. So it's not explicitly chosen, but we know that the C in the previous formula can be made smaller if we learn a more stable filter So what we want to do is we want to find a way to like bias the filter that is learned to be more stable. And one interesting thing we can do is we can look at the system physics to try to bias the learning. So I have said we should consider two examples or two GSOs with the following spectrum. If you have two GSOs, the first has like a linear eigenvalue decay, and the second has exponential eigenvalue decay. In the case of the first GSO that has a linear eigenvalue decay, so the rate of decay between consecutive eigenvalues can be given in that way. You can learn an integral Lipschitz filter, but it's harder to satisfy an integral, the condition for an integral Lipschitz filter compared to the second GSO, where you have rapid decay of high frequencies in the eigenvalues spectrum. So you're more likely to naturally satisfy integral Lipschitz condition with a smaller c if the GSO has this kind of spectrum, exponential decay. So, what we are showing in this graph is we're looking at two GSOs. So the GSO that is popularly used in graph neural network, for example, is the normalized adjacency matrix. And another GSO that can be used, for example, in power system is the power network susceptance matrix, which is the B matrix, for example. So what this plot signifies is you have the adjacency matrix. If you look at the spectrum of the normalized adjacency matrix for this power system IEEE 39 bus, it looks like this. Now, if you perturb the IEEE 39 bus, that is, if you randomly remove an edge from the network, while making sure that the network does not become disconnected. So if, for example, if we select a line that separates or makes the network become islanded, we don't consider that. So we consider only lines that when you remove the network can still be connected. So if you look at the eigenvalue of the network, or if you look at the spectrum of the network, it looks like this. In the case of the 39 bus system, when you're considering like the normalized adjacency matrix. But if you look at the susceptance matrix of the power system, the B matrix, the spectrum looks like this. So the spectrum has exponential decay in the case of n-1. So the full network is what is shown in broken black lines, and the n-1 cases are the many colored lines. So if you look at other networks, so for example, IEEE 300 bus, it exhibits like a similar structure. And this is maybe not exactly linear, but it's almost linear in the case of the normalized adjacency matrix. But if you look at the eigenvalues of the B matrix, which is the susceptance matrix of the graph, you have the same property. And you have the same property as well in a very large grid. So IEEE 1354 bus. So like from what we can see, the property holds across different, let's say, transmission level networks. So 39 bus is small grid, 300 bus a medium grid, and 1354 bus a relatively large grid. So that becomes interesting because that suggests that maybe we can use the B matrix as the GSO in learning our graph neural network. So the research question, and this is still like an ongoing work, the research question we have is if we use the physics-based GSO, so if we use the susceptance matrix of the power network, can we learn a more stable graph neural network? So is the physics-based GSO more stable to n-1 line contingencies when we're predicting ACOPF solutions? So in ACOPF, AC optimal power flow, what we are predicting is power injection, real and reactive power injection in the case of the power system. And we're also predicting voltage at the bus. So we're predicting voltage magnitude and angle. So with these two things, with the real and reactive power and the voltage magnitude and angle, we can derive through power flow equations, we can derive the line loading. So we don't need to predict that. And we know already from our knowledge of power system that voltage output is topology dependent and exhibits strong locality property. So in other works, they've used like just graph filters to get voltage measurements. It's because of the strong locality property that voltage measurement exhibits. And if you think of the dependence of the voltage magnitude, especially on the B matrix, the susceptance matrix of the power network. If we think of fast decoupled power flow, which is just like an approximate power flow, the B star and the B star are modified susceptance matrices in the case of fast decoupled power flow. So this gives us an intuition that the B matrix, we can consider the B matrix, the susceptance matrix of the power system, as an underlying GSO that helps propagate voltage information across the grid. So it's a very small case study. We've used data. So there is a large-scale ACOPF data that was recently released by DeepMind. So we considered the medium-sized 118 bus grid. And maybe I'll explain a little bit the benchmark. So we used like a vanilla, just fully connected neural network, so feed-forward neural network. Considered the message passing GNN with normalized adjacency matrix. So what is typically done, the adjacency matrix as the GSO in the message passing. And then we've considered message passing GNN with the B matrix, so the susceptance matrix of the network as the GSO. So the results are in three settings. I just call them A, B, and C in this case. So the one of the key points is that you can use a feed-forward neural network to learn ACOPF solutions that are reasonably accurate. But the problem is the scaling behavior, as Jochen also mentioned, the scaling behavior of such neural network. So in this case, for example, the feed-forward neural network has 1.2 million parameters for 118 bus system. Now, even from the literature, as you go to larger and larger grids, it becomes problematic because the size of the neural network will no longer fit in your computer memory, as you need millions and millions of parameters. So the three cases or the three settings in which the results have been presented, A, B, and C, is that, so we consider a case where we learn a GNN on the full topology. So we don't consider N-1 cases. So the GNN is learned on full topology, and the test set also contains graph with the full topology. So no, we don't have N-1 cases. In the second case, we have N-1 topology. So the training data contains data set, ACOPF data set, where random edges have been perturbed. So you have N-1 cases, and the test set is also the same. And in the third setting, you trained your model on only the full graph, so you don't have topological variations. But in the test set only contains N-1 cases. So those are the like the three differences. So this is the result in the case of like a fully connected neural network, and the results are comparable to what we have in the state of the art right now when you're predicting ACOPF solutions. So in the order of 4⁻⁻3. But what is maybe interesting is that you can see the variation if you learn a network on on the full topology and you go to n-1 case, you have it might not seem significant because of the metric, but in terms, if this is changed in terms of cost, because you evaluate ACOPF at the end of the day in terms of costs. So if you evaluate this in terms of cost, it can be quite significant. In the second case, where we're using just the graph neural network with the normalized adjacency matrix like it's typically done, we can see that compared to the previous one, and there will be a final slide that shows everything in a graphical form, but compared to the previous one, if you learn the GNN on the full graph and you test the network on cases with n-1 topology, you can still see that there is like a significant change in terms of like the accuracy of the model in this case. And then finally, but there is an advantage to using GNN even in this setting, because in the previous example, I showed that you achieve these results with 1.2 million parameters for the model. But in the case of GNN with 86,000 parameters, so less than 10% of in the previous case, you can get comparable results, or sometimes even better results. Like in this case, it's better compared to the previous one. So this is the case where we use the A matrix, the normalized adjacency matrix as the GSO. Now, using the information we had before, if we consider the B matrix as the GSO, so the susceptance matrix of the power network as the GSO, we get comparable results in case A and B to the previous one. But you see here that if you train the network on the full topology, but you test on cases with only n-1 topology, you can see that the network is significantly more stable than in the previous cases when you're training on SIN topologies for the power network. Yeah, so this is just the result visually. So this is on log scale. You can see in the case of fully connected neural network, it's of the order of 10 raised to the power -6, 10 raised to the power 6 rather, for a medium-sized grid really. And you can significantly cut the number of parameters by using a graph neural network. But in addition, the graph neural network with the second GSO, so by using the B matrix as the GSO in this case, so GNN with the GSO2, you can see it's more stable in the case where you're learning on full topology and you're going to n-1 cases in your test set. Yeah, so in conclusion, you can use a graph neural network to learn fast approximate solutions to ACOPF, and you can have significantly better scaling behavior in the case of GNNs compared to just using fully connected neural network. The choice of the GSO may affect the stability of the GNNs to perturbation. So like I said, you want to have more stable graph neural network for at least currently for n-1 cases. And the use of physics-informed GSO may improve the stability of the GNN to topological perturbations. So thank you for your attention.